Greetings again, my amazing viewers. Totally amazing here, the home of scientific knowledge, truth, discovery, research, and the universe, since the 1st of January 2K19. And here we are with part 2 of this flat Earth debunk of the sort of sun and the moon model that their conjecture seems to spout. And let's just dive straight in. You see on the Flat Earth Society's webpage, if we zoom in, we can sort of see their purported model. Here we are, where the sort of binary system that they have, the sun, the moon, the sun, the moon. Yes, right. Well, let's try and explain this this sort of interesting heap for what it is. Now, let's just say then that the sun and the moon are 32 miles in diameter at a height of 3,000 miles. This poses something of a problem. That must mean that the moon is a failing, malfunctioning star. Now, okay, I heard one flat earther turn around and tell me, well, the moon is bright, therefore it's emitting energy. Oh gosh, here we go. Alright, so basically what they're now proclaiming is that this is a binary format. Now, binary stars do actually exist in nature. Let's just sort of zoom back out. And certainly within the Proxima group and the Alpha Centauri group, we have evidence of this. Yes, binary stars are indeed common. This, however, is not. Let's have a look at one of the main problems with this. Okay, in a binary format such as this, these two objects would eventually start coming together under their own mass and obviously would then collapse into one point. Now, what we do have is, if we look at what a supernova is, let's have a look at what a type 1 supernova is first, and why such a system like this could not happen, given the fact that these objects are 32 miles in diameter. So firstly, type 1 supernovae lack a hydrogen signature in their light spectra. Well, firstly, this is a problem because we can take observations of our sun and we realise that there is actually hydrogen that's generated, and the moon doesn't emit any hydrogen whatsoever. But let's move on. So type 1a supernovae are generally thought to originate from white dwarf stars in a close binary system. As the gas of the companion star accumulates onto the white dwarf is progressively compressed and eventually sets off a runaway nuclear reaction. Inside that eventually leads to a cataclysmic supernova outburst. Now, astronomers use type 1a supernovas as standard candles to measure cosmic distances because all are thought to blaze with equal brightness at their peaks. That's not what's happening here. Now, type 1b and 1c supernovas also undergo a core collapse, just as type 2 supernovas do, but they've lost most of their outer hydrogen envelopes. Now, back in 2014, scientists detected the faint, hard-to-locate companion star to a type 1b supernova. This search consumed 2 decades. So 2 decades of research went into this, as the companion star shone much fainter than the bright supernova. This is a problem. We clearly don't see this happening above us, and unfortunately, the sun is not 32 miles in diameter. If it was, then surely we would be in the midst of a supernova. We'll have a look at what supernovas are just now. First of all, we need to look at how stars actually work. Now, there is a specific branch of science that caters for this, and it's called nucleosynthesis, or nucleosynthesis, and it's a specific branch of science that's in relation to astrophysics and chemistry. Here I've found something for you to have a look at, and this is how stars typically will burn through their fuel. So we have hydrogen, which is obviously being consumed, which is then obviously it goes through the fusion process, which generates helium, which then turns through to carbon. Then you get oxygen, so it's a heavier and heavier element, eventually silicon, magnesium, and then obviously iron and nickel being generated, at which time when a star starts trying to produce iron, it's pretty much game over. The core collapses underneath its own mass and underneath gravity, and a star essentially explodes into what's known as a supernova. Type 2 supernovae look like this, if you'll be able to see that. Probably not very well. There we are. Now these type 2 supernovae, which are also pretty common in the universe, are anything above 3.5 solar masses, where 1 solar mass equals that of our Sun. So of course hydrogen, helium, carbon, and then obviously you're then going into oxygen, silicon, and eventually iron. For a 25 solar mass star, this is generally the process here, so hydrogen to helium is around 7 times 10 to the power of 6 years. Then it converts helium towards carbon, which is 7 times 10 to the power of 5 years. Carbon into oxygen, which takes around 600 years. Oxygen into silicon, which takes around 6 months. Silicon to iron, which is 1 day, followed by a core collapse. Now this is a substantially large star, 25 times that of our Earth. Now, when a star actually does explode on its final moments of life, yes, it will blow off its outer shells, and basically then you end up with essentially a remnant left behind. That remnant would be obviously a neutron star, and if it starts rotating massively, you end up with a pulsar. And pulsars emit off their poles, and they can rotate in numerous gyroscopic manners off of each pole. Typically high energy beams are given off, and those high energy beams are extremely hazardous to anything within light years. Now, if such a supernova was to happen, whether it be a type 1 or a type 2, if this was to happen within light years of us, that would be indeed very bad. But let's have a look at how type 2 supernovae work now. And these are the more exciting and typically what you tend to see on various science documentaries. So for a star to explode as a type 2 supernova, it must be several times more massive than the Sun. Estimates run from 8 to 15 solar masses, but you can get them, I suppose, as low as 3. Like the Sun, it will eventually run out of hydrogen and then helium fuel at its core. However, it will have enough mass and pressure to start fusing carbon. Here's what happens next. Gradually, heavier elements build up at the centre, and it becomes layered like an onion, like what we actually saw here, and here, and also here, like the lovely drawing that has been put through to you. So as we said, gradually heavy elements build up at the centre, and it becomes layered like an onion, with elements becoming lighter towards the outside of the star as those elements begin to be drifted off. Hydrogen being the lightest, as we can see, followed by helium. Carbon is lighter than oxygen, and silicon is obviously lighter than iron. So these begin to drift off, and sort of lost as its outer shell. And then once the star's core surpasses a certain mass, which is the Trandeska limit, the star begins to implode. And for this reason, supernovae are also known as core collapse supernovas. The core heats up and becomes denser. Eventually, the implosion bounces back off the core, expelling stellar material into space, forming a supernova. What's left is an ultra-dense object called a neutron star, a city-sized object that can pack the mass of the Sun in a small space. That's a city-sized object, which typically is going to be below 32 miles. Now, there are subcategories of type 2 supernovas. These are classified based upon their light curves. The light of type 2L supernovas declines steadily after the explosion, while type 2P's light stays steady for a time before diminishing. Both types have the signature of hydrogen in their spectra. And stars much more massive than the Sun, and we're talking around 20 to 30 times, might not explode as supernova. Astronomers think instead they collapse to form black holes. And this is the problem. Stars indeed do this, and this has been observed since way back into antiquity. Now, the history of supernova observations we can just take a quick look at now. And various civilizations have recorded this sort of stuff way before the telescope was invented, and the oldest recorded supernova is RCW 86, which was actually seen by ancient Chinese astronomers way back in AD 185. And this was visible in the sky for around 8 months, according to, well, NASA. And of course, before the early 17th century, when telescopes became available, only 7 recorded supernovae happened that we witnessed, according to Encyclopedia Britannica. Now again, what we know today as the Crab Nebula is the most famous of these. Chinese and Korean astronomers recorded this explosion back in their records of 1054. And southwestern Native Americans may have seen it as well, according to rock paintings seen in Arizona and New Mexico. The supernova that formed the Crab Nebula was so bright that astronomers could actually see it during the day. And indeed, other supernovae that were observed before the telescope was invented occurred in 393, 1006, 1181, 1572, and that was also studied by the famous astronomer Tycho Brahe, and 1604 as well. Brahe wrote about his observations of the new star in his book De Nova Stella, which gave rise to the name nova. A nova differs from a supernova, however both are sudden outbursts of brightness as hot gases are blown outward. But for a supernova, the explosion is cataclysmic and signifies the end of a star's life, according to Encyclopedia Britannica. Now, the term supernova wasn't used until the 1930s. Its first use was by Walter Baade and Fritz Zwicky at Mount Wilton Observatory. He used it in relation to an explosive event they observed, called S Andromedae, also known as SN, or Supernova 1885A, after the year or around the time it was discovered. It was located in the Andromeda Galaxy, and they also suggested that supernovas happen when ordinary stars collapse into neutron stars. Now, in the modern era, one of the more famous supernovas was SN 1987A, of course, from which 1987 was the year it happened, which are still being studied by astronomers because they can see how supernovas evolve in the first decades after an explosion. So the first first 5 stages in the death of a star, let's sort of zoom in and have a look at this. So number 1, just before an explosion, a red supergiant star approaches the end of its life. There's no more fuel to burn and make it shine. In other words, the reactions, the nuclear reactions within it, fusion reactions, can no longer really continue. Soon its massive dense core is bound to collapse under its own weight. Now the first flash, you get this as the core collapses and sends a shock wave out. Basically, it all collapses in, and the first shock wave as it bounces off out of its central core. For a few hours, the shock compresses and heats the envelope, thus producing a very bright flash of light from inside the star. And 3, once the flash is gone, after hitting the surface, basically once the core collapses in on itself at 50 million kilometers per hour, the shock blows the star apart. The core turns into a neutron star, a compact atomic nucleus with the mass of the Sun, but only around 10 kilometers in size, or just under 5 miles. Then we have the proper supernova, which is the hot glowing surface expands quickly, making the fireball brighter again, and in just a few days it will be 10 times the size of the original star and will be discovered by supernova hunters and visible way, way, way across the universe. And then number 5, a long time after, the remains of the former star are spread over light years of space. They keep floating quickly, sweeping up interstellar gas here and there, leaving behind a faint, beautiful glow. Now, when it comes to heavy elements, those are indeed produced in the final dying seconds of a star's life, and in fact right down to the final millionths of a second, which is then when you start to find things like gold, platinum, uranium, and other elements formed. And that is essentially how supernovas occur. Let's just sort of zoom down. And of course, in order for this process to happen, a star to collapse down to something the size of a neutron star would have to be in order of magnitude much more massive than what the Sun actually is. Now, thankfully, our Sun is not going to go that way. It's just simply not big enough, doesn't contain enough mass to do this. Now, theoretically, there's been some research to say that Jupiter, the major gas giant, the biggest planet in our solar system, could have actually become a star. But in order for that to do so, it would need, with its current composition, over at least 1,500 times more mass and size than it has. Now, deuterium, which is also made of a variation of standard hydrogen, which is also known as heavy water, could, in theory, if Jupiter was made of deuterium, could indeed collapse then and start to fuse, and that would indeed become a white dwarf star or some dwarf. However, again, this throws up more problems for the flat Earth theory, because unfortunately there is no known fusible material that could collapse to around 32 miles that would be able to sustain a reaction like this. Not to mention that such a fuel would not only have to be very economical, but unfortunately the mass of this just couldn't happen. 32 miles in diameter is just not realistic. It would simply, even if it could, exhaust through its fuel supply too quickly. Now, the dangers of a supernova, well, unfortunately, if you're anywhere within 50 light years of one, you better watch out. These things are incredibly dangerous. If a supernova was to go off anywhere near Alpha Centauri or Proxima Centauri, our next nearest system, around 4.7 light years away, well, we would have major problems. Just the shockwave alone would vaporize potentially our solar system. And if anything was to go off in our solar system like this, well, then it's pretty much goodbye everything. This poses something of a serious problem for the flat Earth model. For that to happen, well, unfortunately, there's only really one of two outcomes. Either the so-called binary system they depict here must have already been there, in which case then we happen to drift into its plane, which debunks the flat Earth theory anyway about moving upwards or anything like that, because apparently the whole universe is moving upwards together. So that would mean that either we've had to come into its path, in which case then we surely are the ones moving and the sun and the moon are stationary, which is not too far off our current working normal model, or somehow these two have actually been pulled into Earth's gravitational field, which also poses the problem where a binary system like this, if they're proclaiming that these are indeed the sort of size and mass of a neutron star and fueled off of anything like deuterium, well, for that to happen, and it still continue to give off the energy and light that it is, would mean that it would have to have a mass and a density much greater than ours. Again, this doesn't work in reality. Now, of course, my cynical reply to one such flat earther, my reply is, after they turned around and said, you are aware that the sun cannot be a glowing ball of gas, right? Well, I turned around and said, of course, it's an oversized diesel generator that's constantly being filled with some cheap knockoff momentum gasoline by some invisible psychopathic sky mage who covered our flying space pizza planet with a transparent plastic cloche, and the other stars are just those cheap, crappy, fluorescent light bulbs. Now, given our perspective and our size relation, that would actually mean that Saturn is the size of a small family car, that Jupiter is about the size of a double-decker bus, and if the maths of perspective also serve right, that makes Andromeda Galaxy about the size of a small bar of chocolate. So am I close to getting this? Well, by their anticipations, probably not. But anyway, just to sort of summarise it, this is just pretty much how nuclear reactions within a star take place. I'll leave you with some images. And as always, thank you again, dear lovely viewer. Hopefully somebody from the Flat Earth movement would be able to explain just what the sun is apparently made of, just how on Earth it's meant to be 32 miles in diameter, when that's much, much more considerable in size than any sort of neutron star could conceivably be. And how does a neutron star, like what they are proclaiming, not actually collapse even further under its own mass and become a black hole? Why is there also no evidence of any such stellar explosion happening anywhere near us? And I certainly look forward to them providing, if it is a type 1 supernova, just when that would happen. Answers on a postcard, please. And until the next time, dear lovely viewer, stay totally amazing.